Okay. There's quite a bit of lag, like 15-20 seconds, at least for me. So I had lunch, and let's continue with this first naive implementation. So we have all the required stuff now by the book. Vector quantizer, nice. Let's create our VQVAE. Again, it's switched to the English keyboard. I'm gonna skip the latent dim parameter. And of course we'll have our encoder. I will define the latent dim here as D. Latent dim, it's fine. 512. Encoder expects channels. Just gonna use this. Which I'm going to pass it here. Channels list of ins. So that's channels. Latent dim. Okay, fuck it, use it here. Latent dim by default 512. In size, leave it at that. Self decoder. Channels reversed. Latent dim. Rest stays the default, and quantizer num codes, that's gonna be a parameter. It's latent dim, and let's put beta as well as a parameter. Num codes integer, keep the latent dim there, beta with a default value. So what do we do here? We get ZE from the self.encoder X. What else does it output? I guess it's just that. Now this outputs a lot more. So we have ZQ straight through, the VQ loss, perplexity, the codes themselves, and we quantize it with self.vq, the ZE, and we decode ZQ straight through. That's gonna be Y hat. And return Y hat, of course. Let's return, yeah, I mean, can return instead the one from the code book. VQ loss per complexity. Now the codes. Not sure if we even need those. Great. Let's run a training. Define the number of epochs. 100 is a good start. Learning rate. Wow. I'm not going to use an LR scheduler for now. Optimizer torch.optim.adam w, but let's not regularize here. We use the silu. I would be interested in comparing it with the relu, but with the relu and the mesh, but in a different step, because I'm not even sure if this mapping linearly to a fixed latent dim will make sense. So for now, let's just use Adam. And of course, we need our model itself. Channels are these. Num codes. Start with a small number of codes. I mean, the images are not large. Let's start with 256. And if it's shit, then I'll increase it. Latent dim. Yes, keep it at 512. Beta. I just write these out explicitly so I can see what the configuration right away. And we model.parameters. Learning rate LR. No betas, no white decay, no AMS grad. And I just want to print the number of parameters, as always. Divided by 1,000,000. And like this. We have our optimizer. Put the train losses. Should I keep track of? Yeah, why not? So we can visualize it later. This line doesn't like it because cannot assign model. Yeah, because I forgot somewhere constructor, I guess. The super.init is here, and the encoder and the decoder itself. So what's your issue? Ah, yeah, that's exactly the issue. a little bit more than 9 million parameters. Where is this number coming from? Here. For EP in epochs. Actually, let's write the model evaluation first. So we sample, we only have a single X in our data loader, so let's test. Now it's not called data loader, it's called data sets. X equals X, not image, because that's our arrow column. So the name is a bit confusing, but that's the test data loader. And this is a batch of images. So we call our model with X, batch of images. The model will output a lots and lots. But we need Y hat. We don't need this. We don't need the VQ loss. Do we? Yeah, we do. We need the VQ loss. And perplexity. I'm not sure if it's useful to extract it here, but we will. And the loss actually is calculated there. Is that the full loss? It's not the full loss, because this is just a combination of the codebook and the commitment loss, and we need the reconstruction loss. So compare Y hat with the input. And that's going to be, I will write it as recon loss, f.emsl loss. The input is Y hat, our target is X, and the reduction is sum, not mean. Yesterday I ran into that issue when I just used the default parameter, which is mean, and basically it converts to a single blurry image, and wherever I sampled the latent space for the VAE, it basically returned the same image, almost the same image. So it's not good with mean. Let's see, I mean sum should perform much better, and the final loss is the recon loss plus the VQ loss. And we need to calculate an average loss. Of course, this goes with torch.nograd, and switch our model into evaluation mode. We have losses array. And since there's no loss.backward, I'll just push it directly to that array. Now in the end, average loss I will not print anything here, just return torch dot so loss. I don't need to detach it here because there's no grad. And the shape of this, so this should be, if it reduces, this should be a number, but the VQ loss coming from the vector quantizer now this is going to be interesting because this is a mean reduction. I would expect this also to be a scalar. It will complain anyway. So we have a list of scalar tensors. Add them. Yeah. Along dimension 0 and take the mean. So that's average loss per the whole test data set. So before training, let's evaluate our model. This gives insight into whether the weights were initialized properly or if we can further improve the initialization. I can't recall exactly. Andrei Karpathy had a method because first if you initialize the weights like how PyTorch initializes it by default, then you will have this hockey stick shape. And he did something in one of his videos to eliminate the hockey stick shape. So if you initialize the weights better, then you can eliminate this initial big drop and start with a much better loss. I will check once again his video. And initial loss, printf, initial eval loss is initial loss and in this case I like to start it from 1 and we have X in datasets train. Can just copy this basically, copy most of it, but this will become train. Yeah, that's fine, except and the losses, we need to detach it here because this average loss tensor has nothing to do with the training itself, so do not add it to the PyTorch computation graph. And here that's set QST, I believe, yes. Call our model. We have the loss there, we have the final loss here. Let's print stuff. But only if EP mod 10 equals 0 or EP equals epoch, so that's the final loss. In that case, the average eval loss is going to be, we evaluate our model every 10 epochs, and epoch EP train loss. Obviously this is the average train loss. During that one epoch, so not across the 10. I just want to see the average strain loss for that 10th, every 10th epoch. And 4F. Let's make the same here. Eval loss, the average eval loss. And we could print the VQ loss and the recon loss as well. Let's do that. Just add the space here. VQ loss up till 4F. Recon loss. We would need to keep track of those as well. Yeah, it's worth it for now, just to see inside the model more what's going on and where. So that's gonna be recon losses, VQ losses, make it nice, losses, VS, yeah, I am VS, but this is VQ. Average, recon loss, average, VQ loss, align it nicely, recon losses, VQ losses. And yeah, so we have this batch, we appended the losses. Now set the optimization, the gradient set to none, true. There's a lower memory footprint, as you can see. It changes certain behaviors, for example, and then nothing. The user tries to access a gradient and perform manual ops on it. We are not going to do that. Not attribute returns over yes. If the user requests 0 grad followed by a backward pass, grads are guaranteed to be none for params that did not receive a gradient. Okay. Target optimizers have a different behavior if the gradient is 0 or none. In one case, it does the step with a gradient of 0, and in the other, it skips the step altogether. Yes, but what does that change if it skips the step altogether? Because, well, if the gradient is 0, then it will zero out all gradients in the previous layers. Since the chain rule, you multiply it from the next layer as you go backwards. So let's try not setting this to none, because the gradient is 0, then I would say by proper calculation it should zero out stuff. Otherwise, if it skips, it will just leave. If the gradient is 0, then the white change will be 0. So that should be perfectly equal to like not even performing that operation as at all. So that would obviously, because it writes it lower memory footprint and less operations. So yeah, I would just keep it here. And so loss.backward, calculate the gradients and optim.step. Do we need anything else? No scheduler. Zero-dimensional tensor. Because it's a number. So it's not cat. Just make it a tensor, I guess. The next, yeah, right. Still, I left it here. That's pretty big. It's a big number. Meanwhile, I'm going to add my utility functions here. Don't need to code everything all the time from scratch. So, which one was it? Episode 3 was the VAE. Utility functions. Yeah, that's the current notebook. Okay. Now this looks like it's going to be a long training. Only 9 million parameters, but not even epoch 10 after 90 seconds. How's the GPU usage? I have another monitor, I'm going to check it there. GPU 1, 45 Celsius. Memory utilization is 4.3 and 32% overall utilization of the GPU. If it takes too long, then I'm going to just reduce the overall model size. Or did I mess up something and are we running in an infinite loop for some reason? These are huge numbers. I should have divided them. 253, no, 2,500,000. EVA loss is not that bad. The VQ loss, the recon loss. Why are these such? I mean, the recon loss itself is huge. This would take 40 minutes to train. I'm not gonna wait that. So I'm just going to reduce the model size. What was this 250? It was the latent dim. No, the number of codes. If I just make 128, I know it's going to look garbage, probably. But revert back to using relus instead of silus. We can always change it back later. Where was the other one here? Okay, now run everything again. This looks nice, bearded Monokai Terra. It's not so much faster, is it? I should try that CUDA autocast GUI. Damn. Two and a half minutes for 10 epochs instead of 4. What? Why do these look so bad? Hmm. No, I think what I have now is excellent. Let's check how to... So we could try CUDA autocasting. And what it does, it automatically changes types from float 32 to float 16 whenever possible, but I guess you need to use it with the grad scaler. I'm going to import it here instead, because call it grad scaler. It's now torch.amp.gradscaler. So however, the autocast, it's also, that's now just torch.autocast, is it? So I need to import it from two different libraries. Torch.autocast, that's okay, but then it's torch.amp import gradscaler. Scalar.step optimizer safely unscales gradients and calls optimizer.step. Scalar.scale loss multiplies a given loss by scalar's current scale factor. So you use it here, and then you scalar.step and updates the scale for the next. Why do we scale gradients? Yeah, so the scalar you would use when you use torch autocasting, because when you have really small gradients in FP32, and if you convert them to FP16, those will just round to 0. So FP16 can represent half of the precision of FP32. So in that case, you need to scale up your gradients, and it's called the gradient underflow when the gradients get rounded down to 0 in FP16. Obviously that's really bad, because you can't perform white updates with 0 gradients. So for the forward pass, I mean, we can put the 0 grad to the top, but gradients are not used. Are we even converging to something? Like from 700,000 now, we are actually up a lot. It's diverging. It's probably because of my implementation where I project it into the latent dim. But let's add the grad scalar first. So with the grad scalar, let's zero the gradients here. Here. And for the forward pass with torch.autocast, calculate this, and instead of loss.backward we use the grad scalar. Grad scalar dot scale loss dot backward. We use the grad scalar to step the optimizer, which I call optim. And update the grad scalar. And I could use the grad scalar also when running the evaluation with torch dot, not the I mean the autocast. And we don't need to use the grad scalar because we are in evaluation mode. However, the autocasting should still provide speed up. And the recon loss, we are not triggering a backward pass to calculate the gradients, just calculating the loss at the end. So that's fine. We use only y hat and x, so this can come out from torch.autocast. And now let's go back and change this. I'm gonna refer back to this. So if I set a padding 1 with a 3 by 3 kernel, so this is the kernel size, this is the stride, this is the padding. If there is no padding and we are using a 3 by 3 kernel, then the size will be less than the original by 2 pixels, but we extend it with 2 pixels and we run that, so this here will keep the size. Which means the end result will have, of course, the batch channels -1. This is the output channel, that's D, or the latent dim. And the H and the W will be the smallest dim, because it keeps the size of the last. So right now we don't need this here. And don't need the linear layer and an unflattening here, and this will be not channel 0 but channel latent dim. Of course, we don't need to unflatten, we don't need this, and therefore we don't need this. Let's see if we can run this. Yeah, I would have been surprised. So given transpose 1, weight of size expected input 1 to have, but got 5 to have channels instead. That's right, because the number of channels, the first layer need to be latent dim. So we need an extra conv2d in place of the linear and the non-flattened layers, just as we added it in the encoder. That goes from latent dim into channels 0. Again with kernel size 3 and stride 1 and padding 1. And then now we are good. However, here, now this changes a lot. And I will grab this opportunity to rename my Z. And do it by the book as. So let's extract the dimensions from ZE. It says Z equals ZE, we permute it, contiguous to -1 D. So we have BD HW, and when we permute it, we keep B, that's gonna be H, the third is width, and one is D. And then we view it as BHVW D. I'm gonna remove this one. That's the codebook white. This calculation stays the same, but the shapes won't stay the same, because now this becomes BHW, that's 1K. This shape is, it says BHW K. E2 will be broadcasted, Z2 second dimension Probably so the shape of, I'm not sure anymore if these shapes stand. And what it does here is that codes, that's fine, and the ZQ will be of shape. Actually, we need to add some more. View it as, I mean, I'm interested in this shape. Print ZQ. And then we reshape ZQ. We view it as BHVD, because the first three axes are just squashed now, so move them into separate dimensions and permute it back. 0, 3, 1, 2. So that's gonna be contiguous memory BDHW. So the number of channels here is the latent dimension, and in the latent space we have, so H by W is an image, which is now a small image. And the D contains these images. So if our latent dim is huge, then for each sample this will be like this will be small images more than 300 times. So let's, what if we just say 64? I don't think it will converge to something meaningful, but the training at least will be faster. Back where we were. ZQ. So codebook loss moves the encoder gradients, which is now ZE, and I also have a Z that's not good at all, because very typo prone. ZE closer, and the commitment loss moves the codebook closer to ZE. And in this case, it's ZQ and ZE. Now, perplexity calculation doesn't involve that, so I guess safe to run this. Not enough values to expected for GOT2, yes, because my example is not made on that. Assume the single vector. That's definitely not enough. Upscale channels. Yep. num codes, the latent dim could be a bit bigger. That's interesting. We greatly reduced the number of parameters to be trained by not using that linear layer and using this convolution instead. So that's pretty good. So that's d times 16. 16 is the full image size, because we scale it down to 4 by 4, multiplied by d, which is 300 something, and previously it was 512, but we had another layer, a matrix, that mapped from 4 by 4 times 512 like this. Okay. Autocast doesn't work, or device type. Device type. Oh, yeah, well, can't I set just the device itself? And I could use just like this. Torch.autocast device type CUDA. Without this one, that's good. But I didn't set the device type there. And too many prints. Let's remove the debug logs. Now what I would like to see as well, if this training converges anytime, anywhere, is I would like to plot the evolution of the codebook in that latent space mapped to two dimensions. I didn't move X to the device. I didn't move the model to the device. So it's training on the CPU. Okay. Should input type float and by, well, you're casting yourself. Okay, let's move it here inside, maybe it will auto cast that as well. No, it doesn't. Let's set the eval. I need to move it to device here as well. Is it really this slow? Well, it's faster. I mean, it was 30 seconds, so 3 and 5 minutes for a training. That's quite all right. But the recon loss is huge. It's not going to cut it because we are adding together the recon losses with some reduction and VQ losses with mean. So they are not in the same league at all. So it's just not going to train the model only basically based on the reconstruction loss. I mean, I received error that the bias and something else should be of the same type. One was half precision, so that at least it means that the autocast does work. So the initial loss is still huge because I didn't change this, but in the training we can see some progress, I guess. I have the utility functions here. I just need to import matplotlib or import matplotlib.pyplot as plt. And while that is training, I'm going to model.eval def reconstruct image x. It's torch.tensor. Set the model into evaluation. Torch.nograd. Model x. Now model returns 4. variables, and x dot squeeze at 0 to the device, because we are taking it from the data set, and y hat im show y hat squeeze at 0, and it does move it to the CPU and permutes the channels. But let's show the original image as well. X. In this case, that would be, yeah, that we can keep it like that. So let's pick an image from data sets. Let's check the train data set first, up to 5,000 images. This one. Reconstruct image img. And I should log the perplexity as well, otherwise perplexity perp 4. And I'm logging the wrong values here. Average recon loss and average perp it will be. So perps and average perp, and add it to the array as well here. So perps, perplexity detach, and this is going to average perp perps because our codebook might just die. However, yeah, so it's not going anywhere. The recon loss is, this is not converging, man. It's the average perp. So we can just take the vector quantizer out of the picture. To arrive at a single autoencoder. Debug our code. I mean, I'm pretty sure it's the vector quantizer, but let's just humor ourselves. So we have the decoder. We will return, it's gonna be y hat. ZQSDB equals perplexity, set them to just 0, 0, 0, 0. So we have a normal autoencoder now without the linear layer that I used to have for the previous ones. And yeah, it doesn't have, so these would be actually tensors. So grab them as torch.tensor. And yeah, it's long, well, it's gonna be a long line. 0.0, try like this. that converges good. So the quantizer returns VQVAE and we decode that. That would be there's a lot of debug code here. I'm just gonna remove them so we see clearer. And rename this to ZQ straight through. Double checking everything. I definitely made a typo somewhere, or I misunderstood something, but so we have the encoder. We encode z.shape will be this in the case when we have 512 as the latent dim. And those channels, so it's an 8x8 image. What did we use? The actual, I think we used the same 64, 128, 128, 128. Should be an 8x8 image as well. A uniform init. That's proper. That's Z2 plus minus this. Should the order matter because of broadcasting? Z times ET. So Z is now in the shape of BHVD and ET is KD, but then it becomes day key. So BHVK will be this shape, and this shape Z2 is, since Z is BHVD, that is 1 K. So if I add these together, they might just broadcast. So this broadcasts to K and this broadcasts to BHW. Then we pick the minimum argument along dimension 1 in the disk, so along K. from the distances. It's always interesting to me when we just squash the batch into a single axis with the samples themselves. So ZQ, that's PHBD, that's fine, we permute, contiguous. Now if I was wrong and in fact check the Dodge.mslos, it's called mean squared error because the reduction is mean. Otherwise it would be the sum squared error. But the sum squared error worked really good for the VAAs. Lessen the code, shorten the code, just use it like this. And now we should be able to reconstruct, but this is a normal simple autoencoder, but without the linear layer. I don't think it even matters if I bump up the number of channels, because in the end it's 8 by 8. Maybe if I bump up this one anyway. Let's go back to what we actually do. Have 512 codes, 8024 codes. Yeah, that's, yeah. And train. Okay, so far so good. That's lower than the initial loss. So we have a convolution from this many channels to this many channels. And 8 by 8 images or feature maps. Latent dim times the number of pixels. Ah, yeah, nice. It's converging now. So the perplexity num codes is 1024. But the issue is that the perplexity is larger than the codebook size. If all k codes are in perplexity equals k, but my k is my perplexity is larger than the k, the codebook size. That's not a valid perplexity. I don't know, this looks like a very small number, but it pushes the perplexity. If I remove that, but the average shouldn't be, this is just way too small of a number to cause that, I would say, but I see no other reason. Let's try reconstructing with this. I don't know. I mean, the codebook was definitely overused, which means for all these faces we only have 1000 tokens. Let's bump it up. Model is now 3.5 million parameters. But hey, this is the first image I made with a vector quantized variational autoencoder. And I want to plot from, so I think it's called TSNA, from Scikit. I use it very frequently. Let me just check the previous. So here, yeah, we did that. This is the code I want. But the import sklearn manifold. It's a lower dimensional continuous space in a higher dimensional space. So sklearn manifold, and I can gather the latents. And with this TSNA, we can plot it in 2D. Now, this I can hardly remember, so we can create a figure with fixed size, and then the latents in 2D we'll have, we take all x, all y's, not sure what that is. Let's show a grid, and I want to create actually an animation of the codebook vectors mapped into 2D, how they actually move around in that latent space. So from sklearn dot manifold import TSNA. Matplotlib is already imported as pplot as PLT. So for each epoch, it should be enough. So codebook weights. So these are the codebook vectors in each row. This is a matrix. Should I average their position, it would be more accurate. So that's EP codebook weights. Perform the forward pass. Now the weights might be casted here to half precision. So I'm not sure if I can do this, but let's try first and see if we run into an issue. Model.vector quantizer dot codebook dot weight. I want to add that to codebook weights of this epoch. After the epoch, I add to codebook weights torch.tensor EP codebook weights dot mean on dimension 0. So we have the discrete feature latent vectors like this. This is the codebook size, so as many feature vectors as codebook size. And now we are packing together these matrices. This is dimension 0. And we perform an averaging on each number. So that's going to be the average codebook weights for that epoch. And now we have a list of all codebook weights for every epoch. It's logged here. Training finished with that large codebook, so let's check. It's not any better. And perplexity is still really high. Like, how many tokens do I need for this? Set for 8,000. Or I just up this, keep that. How many million parameters? That's 10 million. It doesn't like it. Converting it requires gratitude to scalar mate. No. No, I want to detach it. It's an array, yeah, wrong place to detach. Detach it here. Well, the weight is a matrix. EP codebook weights. So list of matrices converted to a 3D tensor. Only one element tensors can be converted to. I don't want to convert it to a scalar. Yeah, it looks fine. Cat it then. Well, the cat worked. But stack it. Yes. 21. 21 times it pulled the batches from that. So if I stack it here as well, and then mean along dimension 0, I should end up so torch the tensor worked here because the losses are numbers, but these are matrices. So the codebook is pretty large now. Nah, the perplexity cat. Nah, that's not. That surely isn't good. Is latent dim used anymore? Converse, we can up this to 1000 and keep this 8000. That number. Now train. Get back to this. So we have our codebook weights, and it's in the shape of epoch KD. That's the average for that epoch. So what I want to display is the K vectors for each epoch. So let's just take go through EP in range epochs. But TSNE takes a very long time, so I'm going to break at the first step, just trying now to visualize it. Components is 2, yes. Perplexity, it's a different perplexity here. It's the default 30, that's good. And iter max we need to set, I think it's called n iter max or n max iter, max iter. Max iter has to be greater than 250, I believe, or at least be 250. That's TSNE. And PRT.figure fixed size, that 86 was good. PRT grid true. PRT show and PRT scatter it was. X, what does this return? TSNA dot fit well, codebook weights. Why is my perplexity always so high? It's the only question I have. It should be around 80% of that. So 6,000-7,000 would be great. I'm gonna have to peek here. Fit transform and the latents were moved to CPU. Fit transform. This I need, yeah. Let's move the whole thing. I mean, it's an array, so I can do codebook weights EP to CPU. That's all, and you get a 2D array. Yeah, like the init PCA and random state, like what are the default parameters for that? Init is PCA. And the random state is none. So I'll just show the first element. It's almost finished. And I want to go deeper into the math side of how it is done. I mean, this is a really cool trick, a lot to learn from it. It's just a mean squared error, but if you detach, then this cannot be adjusted. And in the other equation, this cannot be adjusted by a backprop, so Yeah, so this is basically the SG in stop gradient, and via backpropagation this is treated as a constant. And when you're backpropagating, then the gradients only flow into the codebook embeddings. That's not true. If I Damn, you're ugly. Let me just flip these, because according to the original paper these are ordered like this, and now I can check whether, so beta, it says it's for the commitment loss, and the stop grad is on the embedding in the commitment loss, and the codebook loss is the other one. And in the codebook loss, codebook loss is fine. The detach happens exactly the opposite way according to the original paper, but ChatGPT fucked up its original implementation. So now I just really want to find the original VQVAE paper from 2017. And we are going to check it together here. So neural discrete representation learning, last revised May 30, 2018. Where is the loss function? Those are experiments, and Pixel CNN Prior trained on frames captured from DeepMind lab. Here is the loss. To make sure the encoder commits to an embedding and its output does not grow, we add the commitment loss, the third term in equation 3. So beta by the commitment loss, Z embedded stop grad. So beta by the commitment loss, this is the Z encoder, and according to the paper, they stop grad on the embedding. ZQ is the embedding. How do I copy the latex code from the PDF here? I guess I can't. So here is the full loss. This is the reconstruction loss. The log of it, not mean square error. Or for instance, but the key what we're after is beta. We have the commitment loss, the third term in equation 3, this one. So beta by commitment loss is fine. ZE that's the MSA mean squared error. Second distance squared, that's MSE. And Z add and stop grad on the embedding. This is fine. This is fine. And on the other case, stop grad on ZE. GPT literally doesn't know what it's talking about. It's good to get started, but right after, just open up the research papers, open up repositories, documentation. Which means that so I detach ZQ here, but now I detach ZE here. So it was the opposite. That might have been why it didn't train, because it was, so with beta the commitment loss is taken into account only 1/4 of the other loss. I'm not 100% this will get rid of our perplexity issue. No, it doesn't. More work to be done. The reconstruction loss here. So the KA term can be ignored because we assume a uniform prior Z. So they use 1024 latents overall, 32 by 32 for ImageNet. What's the size of ImageNet? A cipher 10 is like 15,000 images. And they use 640 latents for that. The resulting loss L is identical, except that we get an average over n terms for k-means, commitment loss 1 for each latent. That's the same guy. Should use only this many. But is there any mention of the dimensionality of the latent space here, or just the code sizes? Yes, and I'd like to see some sample Ds. How did you choose the value for D? $512, okay, that's good. So the space itself is a space by space by space. It's a Cartesian product of three spaces. What we have here in the encoder which means if their latent space was well, that's D. So they say 32 by 32 by 1, so my D would be 1, and they only downscale the images to 32 by 32, not 8 by 8. That might be it, that I downsized the image way too much. So it's gonna be 16 by 16. Let's try this, but then bump up that. I'm at the wrong place, sorry. So it's gonna be 16 by 16. Do it like this. So now one downsizing is 64, and this is their 32 by 32. The num codes were that and the latent in 1. I mean, let's try. So this would mean basically we store 512 32 by 32 grayscale feature maps. AKA latent. Well, I couldn't say latent vectors because they have 2 dimensions. Perplexity is still higher. I'm not sure if it's just the calculation. Perplexity, detach perps, append perps dot mean, average perp. Something's off with the perplexity still. Very, very off. It's annoying me a lot. No, you need to stop. And I removed. Let's see. So the perplexity must be at max the codebook size. Now it's nan, because anytime for a single time it becomes not a number, it will let's write it like this instead, that's better. So the entropy will be So this will be the average probabilities, average use per batch of shape K, and average props equals average props plus a small epsilon I can just add it here, and then slash equals average props.mean, normalize it. Then the entropy becomes minus average props times average props.log dot sum, and perplexity is just the entropy exponentiated entropy dot exp exponential exp. So here they treat D as a number dimensionality of each latent embedding vector EI. The embedding space is KD, but that's not how like you write it here. They use the mean square error as well as the reconstruction loss. Now the perplexity is 0. shit. Typo. I'm getting tired. That's why. You have a code book of 500 and the perplexity is 2, 4. Well, this definitely looks better than the whatever. But the average probabilities weren't normalized previously. I believe I will spend another day with vector quantizer, get deeper into it, plot how the codebook weights move around the space, and do more math on the quantizer part. So from this 4D tensor, it creates a matrix set. We sum along dimension 1 here. That's all set E squared, and we do the same with the codebook weight. So we square the whole codebook, sum along latent dim, that makes sense because the length of a vector is x squared plus y squared plus z squared plus whatever. So we square each component of this matrix, each element, and we summarize along the second dimension, so it squashes into, so each code will have its length squared, and we use this identity Okay, perplexity is growing. It's underutilized. The codebook is underutilized, definitely. The train loss is lowering. Eval loss, VQ loss, recon loss seems fine. Could even train it further. 100 more epochs. Going to try it like this, because it's still lowering quite a bit. The reconstruction loss is stuck. Oh, it's even worse now at this point, so yeah, quickly let's just train 20 epochs more. We can do that because I declared the model here, so it doesn't reinitialize. But I lost the codebook weights. So after a local optimum that we could see at epoch 100, now it's lower. It's a bit higher now, the recon loss. Again, it's going up on a hill. So it's moving around quite a bit on the error surface. So you can see this is a steep jump. Train loss got much better as it started to utilize more codebook entries. Let's train a bit more. Oh, that's much better. And we could train even further. The latent dim is actually just the 1. In this case, the D, as per their example from the research paper. So they downsize the image to 32 by 32 and with a latent dim of 1, 500 codes. But the perplexity, it's just 210, so it's a bit underutilized. What if I bump this up to like 60? That's a lot. 32. And we train for 100 epochs. interesting that actually they are talking about latent space, and yes, all right, it's latent space, but what's happening with latent dim1 is that basically you take these 32 by 32 feature maps, grayscale, and arrange them into this codebook. So it's not like you project the image into some linear, or not linear, but a high dimensional space as before with the variational autoencoder and with the autoencoder. Instead you work with these feature maps or matrices. But of course, I guess this is also adjustable. Like, I mean, I would love to try to flatten all this back as if it was before. Have a linear layer here that like re-enable this with a latent dim of 300, and then we wouldn't need this because it would be anyway batch dim, and the ZQ would be different, but I don't know. This feels like just I mean, if you want to visualize what as an image what's in the latent space, it's cool because you have grayscale, small grayscale images. But if we were just talking high dimensional vectors, because this is a perplexity. I mean, it's pretty good, so it's converging. I could even try reconstructing. So the codebook loss is you stop grad on the autoencoder output. The commitment loss is stop grad on the quantized. So you stop moving the codebook for the commitment. The commitment So let's just remember, like, the codebook loss forces the network to move the codebook closer to the autoencoder input. And the commitment loss forces the network to move the encoder closer to the codebook, which makes sense. So you treat the encoder output as constant for the codebook loss, and you treat the codebook constant for the commitment loss. So it uses 68, around 68 codebook train loss, VQ loss. Okay, is it better or worse? Ha! Now we have colors. I mean, it's still really bad, and it would be worth to. I would be interested in not in exactly with the sum reduction, not a mean reduction. That's one thing, and I'm just going to write it as to do here, and there's, yeah, we could plot that. Missing two, yes, because let's call them latents. The codebook here. Let's go back to the codebook because I need to reinterpret num codes and latent dim. But if I only have one latent dim, as they had in their case, okay. It's not even good to plot it like this. I'm too tired now. Been doing this for like, yeah, almost 6 hours. My brain is fried with the math. So let's just plot something. Oh, one of them is really far away. Codebook, so that's so of shape and samples and features. That's good, that's good. So this is the initial. And if we step through the epochs, so range, what, 0 till epochs with steps 25 and see, and we plot then 4. Interesting, this is interesting. This is basically a list of the latent vectors. I mean, it's a much better reconstruction than the variational autoencoder. Of course, we are working with 32 by 32 images. And a bit different network. I mean, latent dim is 32, but it's 32,000, around 32,000, because we are working with images. So if I were to make an autoencoder with a latent dim of 32,000, then of course the reconstruction would be better. So I'm gonna make a checkpoint of this and a copy of this notebook. And what if I stick to my flattening, and instead of treating these latents as images, I'm going to map into latent dim. So run everything. I need to remove this like this. It works, it's compatible. Now here, this isn't going to cut it anymore, because Z will be just ZE, and I don't need to view again, and ZQ will be just ZQ. Is it working, like code-wise? Now the true latent dimension is 32. It's a single space, a single hyperspace, with a single 32-dimensional hyperspace with vectors in it with 32 components. So the reconstruction quality will be garbage, because in the previous example we had a 32,768 space. And it's diverging because it just cannot find. Now it's kind of getting back. There was a hill, the error surface that it went through. And how many codes do we have? So we have lots of codes. Haven't really started to use those codes. So it takes more time to find it, because we have 32 long vectors, 500 of them. And with those, we need to represent these images. And I would want to scale this down one more time, at least to 16 by 16. To 8 by 8. Stop this nonsense. And actually we have a much deeper network. It's never good. Yes, because the image size is, how was it like this? It's 8 million. Well, yeah, of course. And if I choose like if the latent dim is 512 and we have, it's a huge network. Latent dimension could be 32. It's still bigger. Because we have a mapping to that latent dim. So that's another. Yeah, that's kind of the same. But I mean, if the latent dim isn't at least 3, then we can't even get back true color images, I guess. Or maybe we can. But in the convolution they are added together and averaged. So we downsize to what now? 8, 64, 32, 16, 8 by 8. How many codes did they use in their examples? $512. That's with pixel CNN. So what's the architecture of pixel CNN? Gated pixel, gated convolutions. Okay. So they just replace the decoder with pixel CNN, at least in this example. Gated convolution or layers. Okay. Well, we are not really training. It's using more of the code book. I mean, I should probably leave it training for the night, and when it starts to use up most of the code book, like around 400 or 500, then it might start to converge after like 20,000 epochs. It's a deep network. Also, because it's such a deep network, maybe using a group normalization would be advantageous. But it's training for so long. I'm not even sure if I should stick to this. Or just downsample it to 16 by 16. This looks like way too much. And the latent dim just to be 4 diodes. Yeah. And again I flattened it. Right now it didn't learn anything. I'm just not really okay with having images in the latent space. I want single vectors. I mean, you can flatten them, but maybe I will just do that. I have to refer back to the Gini paper. Now, for now, I will delete this flattened stuff and come on, and stick to this. Great. All right, that's it for me for today.